I am Dr. Mahmoud Abdulsalam, and I welcome you to PLBC Virtual Learning Center. Our topic for today is going to be continuation of modern physics. However, under modern physics, what we are going to look at today is what we call radioactivity. Before we look at radioactivity, it's important that we try to recall some of our previous information we had about the atom. We talk about the atom, the constituent of the atom, which is the proton, the electron, and the neutron. The first thing that we may need to define here is what we call the isotopes. It's expected, for example, if you talk about hydrogen, hydrogen has one electron. Is that true? But it's possible that you can have the same hydrogen but with a different atomic number. For example, we call them heavy hydrogen, deuterium and tritium. So whenever we have the same atom but having different atomic number, we call them isotopes. Is that okay? Is that understood? Now we're going to talk about radioactivity. What do we mean by radioactivity? We earlier talked about the atom, and within the atom we have the positive charge, we have the negative surrounded by negative charge, the proton, the electron, and the nucleus. Is that okay? Okay, the proton, the neutron, and the electron. The neutron is electrically neutral. Okay, for the atom to be stable, there has to be some forces that are into play. Normally, the force of attraction between you and I is just gravitational force. But when you talk about the force of attraction between neutron and neutron and proton, you talk about strong nuclear interaction. At this point, what I will remind you is we have four fundamental forces in the universe: the gravity, the strong and the weak, and then the electromagnetic force. The force that bind the proton and the neutron, the proton and the proton, the neutron and the neutron within the atom is what we call the strong nuclear interaction, the strong nuclear force. Is that understood? It is expected in a normal atom, the number of the neutron and the proton should somehow be relatively equal. The number of proton and neutron in the atom are expected to be relatively the same. But in heavy atoms, what do I mean by heavy atoms? You find out that if you look at the periodic table, there is going to be a point where you can have atoms with atomic number greater than 83. Is that understood? These are the atoms I term as heavy atoms. The number of protons the number is not equal. Either the proton number or the neutron number, you find out that one is far greater than the other. And as such, the atom is not going to be that stable. With time, it starts disintegration. Disintegrating. By disintegrating, after disintegrating, it emits some rays and particles. The rays and particles that it normally emits, the particles are alpha, the electron, and then the gamma. This is alpha, and then the gamma ray. So now I try to describe explain what we mean by radioactivity. The spontaneous, continuous disintegration of heavy nuclei into smaller nuclei is what we call radioactivity. Are we in agreement, please? Are we in agreement? Good. So now, having established what this radioactivity is, I think it's important we try to look at this rays and particles that are being emitted by radioactive elements. I will start with this guy, which is alpha. Is that okay? Normally, to understand their properties, what we try to do is we make them interact with other things. For example, we talk about electric or magnetic fields. Okay? If we have an electric field, then we subject it, we expose this to them. It's expected that we have one of the two. It either deflects or it will not deflect. Is that okay? If the electric field is positive field and we see attraction, okay, but the deflection will determine the charge. Is that okay? So what I'm trying to say is, when this is exposed to electric or magnetic field, we have large deflection. I don't know. Let me look at this. Okay? This suffers large deflection under electric or magnetic fields. It was discovered that this alpha particle are nothing but helium in nature. As I said earlier, they are positively charged. Is that okay? Okay. Another thing that we can do to have an understanding of some of the properties of this is to try and place a barrier on their path and see how they are going to react to the barrier. If you placing a small paper on its path as it's trying to pass, will the paper stop it? If paper cannot stop it, if you put in a metal, will it stop it? And the rest. And that will give us an idea about the penetrating ability of this particle. Is that okay? Then it was discovered after doing that experiment that this alpha particle can even be stopped by a paper. You place a paper on their path and then it will be able to stop them. That means they have small penetration ability. Is that okay? So far, these are some of the properties of this alpha particle. Are these understood, please? And additionally, note, we said these alpha particles are helium in nature. If they are helium in nature, what will happen when an atom releases alpha particle? For example, I can have uranium-235, I think 92, U2, being bombarded by neutron. And then the end product is alpha particle, which is 42, plus what? What's your name? What's your name? Aisha, your attention is not with us. Please be with us. Alright, now let's look at this. After this, this is what we call nuclear equation. Whenever you have nuclear equation, in the same way that you try to balance chemical equation, we balance nuclear equation. Now we have uranium-235 being bombarded with a neutron, it emits alpha particle. And we need to know what is going to be the next products. To balance the equation, what do? We said this is 235, is that true? 235 plus 1? 236. What do we have here? 4. The number here on the top must be equal to the total number at the top here. So now if this is 4, what we need to say is 236 minus 4 is what? 236 minus 4. 232. 92 plus 0. 92 minus 2. 90. So you can write, if you don't know the formula, you can simply write x. Please, is this understood? Yes. Is this understood? What we have is we have some kind of nuclear reaction where uranium-235 was bombarded artificially with a neutron. After the bombardment, it released an alpha particle. So for this equation to be balanced, the atomic number on the right hand side must be equal to the atomic number of on the left hand side. Likewise, the mass number. Is that understood? So that's the reason why we say 235 plus 1, it will give us 236. We come here, we say 236 minus 4 is going to give us 232. We have 232 here. 92 plus 0 is 92. 92 minus 2 is 90. And this is forming a new element. So with this, we can say that whenever an atom, okay, if we don't have this, we only have this which is disintegrate releasing alpha particle. In here, that means what we are going to have is we are going to have 231. Is that okay? Is that okay? So what I'm trying to say by this is, if an atom is going to release an alpha particle, the number here is going to decrease by 2, and the number here is going to decrease by 4. The new atom release. Is that understood? So far, these are the properties of this alpha particle. Please, are we informed about this? Are we okay about this? Now, I think we need to look at an example. This is the equation we're having. Okay, I only wrote this to simplify things for us. What the equation said is, we have an isotope of polonium. Look at it. This is the isotope of polonium. It decays by releasing an alpha particle to lead. We are asked to calculate the total energy release after the reaction. Let's understand this. One of the enormous ways of obtaining energy is nuclear energy. I hope you are aware that in some countries they use this nuclear energy to generate electricity. Is that true? So the energy generated during these reactions can be easily converted into nuclear energy. It can be converted into thermal energy, any energy that you're interested in. Okay? So now we have a nuclear equation, a nuclear reaction, where we have polonium-210 decaying to lead-206 and alpha particle. Look at this. As I said earlier, this was 210 and this is 206. But it means by releasing alpha particle, this decreased by 4. Is that true? And this decreased by 2. This was 84 and now this is 82. Is that understood? So it means whenever we have this decay of alpha particle, it changes the number by 4 and 2. You need to have this at the back of your mind. The next thing now is, How are we going to calculate the total energy release after the reaction? Can you remember E equals to mc square? E equals to mc square. Well, it's one of the most important equations in physics. This. Can you remember it? Okay. But my thought is even people passing by physics class should be able to remember this. Okay, now let's try and do the calculation and see. Normally, there is going to be deficit in mass. This is the mass of this, this is the mass of this, and this is going to be the mass of this. What will happen is the rest of the mass, you see, mass, energy can, okay, the equation that I've just written is known as mass-energy relationship, Einstein equation. Is that understood? So it's the equation that relates how mass can easily be converted into energy. So now we are going to look at, based on this is the initial mass of this. And now this is the mass of this is the mass of this. Ideally, if no energy is to be released after the reaction, the energy of the product should be equal to the energy of the reactant. Is that understood? But if the energy of the product is less than the energy of the, if the energy of the product is less than the energy of the reactant, it means energy is going to be released. Is that okay? So now let's look at this. Can we add this and this? We are going to have 205.97449, and in here we have 4.002603. I'm now adding 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. I don't know. Let me make sure that I'm writing the correct thing. Otherwise, we'll not get the answer. Are we there? All right, now I'm going to add, because this will give me the mass of the products. 9 plus 3 is 12 carry 1, right? 1 plus 4 is 5. 4 plus 6, 10, 0 carry 1. This is 5, 7. This is 7. This is 9. This is 9, 2, 0. All right? This, what I have is 209.98241. 1, 2, 3, 4, 5. And in here what I have is 209.97052. I'm now subtracting. What am I doing? Look, the mass of this plus the mass of this give me this. Is that true? Looking at it, this is less than this. It means there is some balance, the deficit in energy. Is that okay? And that energy balance, the remaining energy now is going to release after the reaction in form of heat. So I'm now trying to calculate the energy release after this reaction. Am I understood, please? Okay. 1 minus 2, I can't. I borrow 1 from here. This is 11 minus 2 is 9. Now this is 3. I can't subtract it from 5. I borrow 1. 13 minus 5, 8. This is 1. 1 here. 8 minus 7. It can't, right? So I now take 1 from here. 18 minus 7. 1. 1. 0. 0. 0. Okay, 0, just 0. Please, if there is any of you with calculator, he can help us punch it and make sure that we are getting the right numbers. Is there anyone who's calculator? You can use your cell phone. Are you with your cell phone? Please start from here, this plus this, and then you simply subtract the answer from this. What's your name? Please use your cell phone, do it. Do you know how to use the cell phone to do it? Okay, use your cell phone so that we have two different. Are you done? What do you have? Is it correct? Is this correct? This one. And when you stop, what did you get here? Bilkisu, help her do it, please. Wait. This is 11 minus 2 is 9. This is now 3. 13 each. Now? Is correct? Alright, so now the number you obtain. Look, this is in unified atomic mass. And 1U is going to be equals to 935. 931.5. Multiply the final answer by 931.5. Multiply this because look, this is now in U. All what we have unified atomic mass. And one unified atomic mass is 931.5. What? 931.5. What? No, she's not punching the calculator correctly. 89. Sorry, let's do this. Are you sure this number is correct? Aisha, is correct? Okay, times 931.5. Can I have the cal, please? Two. I think in here I have 5.358 times 10 raised to the power of minus 3. Can you follow how I did the steps? Can you be able to trace how I did the steps? The question said the isotope of polonium. Do we need to write it here? I thought we can skip this. This is the question. We have an isotope of polonium whose number is 21084, right? They said it decays into lead by giving off an alpha particle. Is that okay? Write down an equation to show the decay. Now we're going to write down the equation. This is polonium. Is that true? They told us that it decays by emitting an alpha particle. And we knew that alpha particle is 4,2He. We know that, right? We know that. It told us that it decays by emitting an alpha particle. An alpha particle is helium in nature. So we have helium here, which is 4,2. Is that okay? So now, they are asking us to write the decay equation. To write the decay equation, we need to balance it. Is that okay? Now, this is 210. 210 minus 4 is what? 2 plus 206. 84 minus 2. 82. They told us that one of the end product is lead. Is that true? So we have Pb. And this is the equation that they said we should write. Is that clear now? Please, is that clear? Alright, now, if this equation is clear now, we have written the equation. Write down the equation to show the decay. Determine the Q value. How do we determine the Q value? The energy that is going to be released after the reaction. How do we do it? Normally, to do it, we now subtract the mass of the products from the mass of the reactants. Which one is the reactant? Which one is the reactant? Which one? Okay. Okay, let's say this. You see, in all equation we have the reactant, we have the product. If two molecules of, okay, let me use chemistry to remind you. We have H2 plus O2 giving us H2O. But normally we have to balance the equation, right? Okay. And now we are having to do it, we need to have 2 here. And then we have 2 here. Is that okay? This is 4 hydrogen, 4 hydrogen. 2 oxygen, 2 oxygen. Is that true? What do we call this? What do we call this? Product, right? So if this is the product in chemistry, this too is the product. So the mass of this product should be equals to, okay, all we need to do is to get the total mass of the product. If the total mass of the product is less than the total mass of the reactant, it means energy is going to be released. And if the mass of the product is less than the mass of the, if the mass of the reactant is less than the mass of the product, it means it's going to absorb energy. Is that understood? So now, this is the product. How do we get the total mass of the products? The masses are given here. It says that the masses of polonium and lead are this and this. So now this is the mass of lead. Is that true? So what if we are, okay, let's say mass of the products is going to be mass of He plus mass of PV. Am I right? The mass of this plus the mass of this will give us the mass of the products. Are you with me? Now, the mass of this is this. I have 205.974449. And the mass of this I have 4.002603. I sum them. Is it correct? Did you try adding them? What did you get? 2. So it's correct. Are you there? What did you get? You get this, right? So advisably, since she's using calculator, what I will advise you is, can you read this number? Yeah, just type this number and then you type minus, you press answer. Type this number and then you press minus and then you press answer. Nine. No, I don't think that's correct. Sorry, let's look at this. This is the number, new number, right? I have 209.982416. And in here I have 209.977052. I am now subtracting. 6 minus 2, 4. 1 minus 5, we take 1. 11 minus 5 is 6. This is 3 minus 0, 3. 2 minus 7, it can't. We take 1 from here, right? 12 minus 7, 5. 7 minus 7, 0. 9 minus 0, 9 minus 9. And what I have here is 1, 2, 3. 5.364 times 10 raised to the power minus 3. Is that okay? Remember, please, is the calculation we did here very clear? Is it understood? Yes. All right. Earlier we said that 1U equals to 931.5 mega electron volts. So all you need to do is to say this times 931.5. Please, did you get this number when you punched the calculator? Sorry, you are with your cell phone. But can you use your, can't you use your, your normal addition and subtraction to do this? I shall stop laughing at her. What did you get? 5 point. Okay, so that means you redo this. Now multiplied by 931.5. .99. So since it's the final answer, can I say that this is 5 mega electron volts? Can I say that? You're talking about 4.96 something, right? I just want to write 5.0. Is that okay with you? Is there anything that is not understood here, please? Is there anything that is not understood? Look, it's better you voice out here so that if there is anything we can still go back. Anything that is confusing, please. You don't have anything, you understood what? Okay? So please, you can quickly copy what we have and then we continue with